I'm Mike Castellano. I'm a professor of agronomy at Iowa State University. I'm going to talk a little bit today about the state's drainage infrastructure, and really beyond Iowa too. It covers the whole Midwestern United States. We don't even think about it very much. Out of sight, out of mind. The vast majority of crop production acres in Iowa and many acres across the United States benefit from a subsurface drainage infrastructure that improves crop growth and the ability of farmers to get in the field and prepare the field for crop planting, maintain crop health, and harvest the crop in a timely manner. That farmer aspect of getting in the field and being able to operate the field in a timely manner is really critical for the production system, not just to get good yields, but also to help install conservation practices, de-risk those practices, things like cover crops, precision nitrogen fertilizer application, these things that require extra passes through the field that we know benefit the environment, but they also increase the risk of the operation potentially sometimes when you have to devote that extra time. So drainage is really important for those two factors, getting in the field for timely operations and also improving the crop growth and nutrient use efficiency once it's growing in the field. Those drains, they increase the volume of the soil that the plant roots can go into. They increase the volume of the soil that can produce nutrients for plant uptake as well. As a result, our research at Iowa State University has shown that farmers actually can achieve higher yields while applying less nitrogen fertilizer. And that's really a great situation when we can achieve that outcome. So today, we're going to talk a little bit about a National Science Foundation project that my colleague Liang Dong, who's an electrical engineer at Iowa State University, leads, and I assist with on the drainage side. This project aims to integrate communities with problems and the latest advances in science and technology to solve those problems. And so one of the problems with drainage is that often drainage infrastructure systems are not optimally managed because they're community resources. Many farmers share the infrastructure, and then it causes uncertainty about who is going to pay to obtain and to maintain and upgrade that drainage infrastructure. So when we think about these drainage infrastructures, an analogy I like to use is a private road. Imagine you lived on a private road. Your responsibility to maintain your driveway is generally paid for by your own money and done at your own will. On the other hand, everybody living on the private road pays into the maintenance and the upgrades of the road that everyone shares on that private road. Drainage infrastructures are very, very similar. Many farmers have their own drainage pipes, often called tiles, in their own fields, and those pipes feed into larger community-owned drainage systems. And the decisions about when and how to upgrade those community-owned drainage systems are complex, and as a result, there are social scientists working on this project as well to help understand those decision points there. This project is really unique because it's led by an engineer at Iowa State University, Liang Dong, who's an expert on developing microsensors for agriculture and many other disciplines beyond. It's assisted by his engineering colleague Xiaobo Tan at Michigan State University, who develops robots that we can use to deploy those sensors into tile drainage systems, which we're looking at right here. So we're at an Iowa State University drainage research farm. This farm, unlike farmer fields, has monitoring infrastructure that allows us to measure the quantity and quality of water coming out of individually, uniquely drained research plots. On these plots, we apply various different agronomic management strategies that we think will benefit both productivity and the environment. And then Liang and his colleague Xiaobo, they can deploy their sensors up and into the tile drains here and confirm what we think is going on from our measurements of the above ground and the soil processes from inside the plot. So exactly what we're looking at here are 3 consecutive research plots that go behind us, and each one of them has a drainage system that goes right down into this what we call a sump here, or a monitoring device that collects the water, and then it allows us to sample that water regularly and measure how much water is coming out of the plot. On farmer fields, what's the application? So many farmers have drainage systems. They don't know where and when they're losing nutrients from the field. By deploying robots with inexpensive, high accuracy, high resolution sensors for nutrients and water flow, we can deploy those robots up the drainage systems and measure when, where, and how much nutrients are being lost. That allows farmers to better manage their field at a precision scale to improve both productivity and environmental performance of our crop production systems. This system will help us understand where on the landscape we're losing nutrients through our drainage systems. Our drainage systems have all those benefits we talked about: improvements in nitrogen use efficiency, improvements in yield, the enabling of conservation practices such as reduced tillage and conservation crops, but drains also lead to significant amounts of nutrient loss downstream. Unfortunately, not every piece of the field behaves exactly the same way. And at present, we can only measure the nutrients coming out at the very end of the pipe. We don't know where in the landscape they're coming from. The robots and sensors being developed by Liang and Xiaobo are going to allow us to determine exactly when and where those nutrients are being lost. So this project, funded by the National Science Foundation, funds the next generation of technology that we use in these fields. These are fundamental advances in robots and sensors that are occurring at Iowa State University and Michigan State University, and eventually we hope will be commercialized and available to farmers across the Midwest to improve crop production.
My name is Liang Dong. I'm a professor in Electrical and Computer Engineering Department here at Iowa State University. My role in this project is a principal investigator. I'm also responsible for developing nitrate sensors for this project, and I also work with Dr. Xiaobo Tan at Michigan State to integrate the sensor on his robot so that the robot can move and travel freely within the drainage pipe. So the robot is going to integrate several sensors on its body. It has a nitrate sensor, it has a water flow sensor, it also has a camera. So the nitrate sensor helps us to see what is the level of nitrate inside the drainage pipe, and the water flow sensor can tell us what is the flow rate of water when it rains. And the robot also has a camera that can see the water level inside the pipe. Robot can tell us what is the drainage pipe function. Is there any damage or is there any blockage along the drainage pipe? For the sensor, we pretty much finished the development. We can detect the water nitrate level continuously over some time. Of course, we are also upgrading the sensor, optimizing the sensor to make it more accurate and with a longevity that can make more measurements continuously. And on the robot side, Dr. Xiaobo Tan at Michigan State has developed a couple of different types of robots, and these robots can move freely inside the pipe, but his main work is on improving the robot performance in terms of its speed and flexibility and power consumption. Also, we want to establish the robot as a robot platform that can sense different parameters inside the pipe. Engineering part is one of the critical parts of the work, and we are also looking at developing analytics tools that can fuse the data from different sensors, including the sensors that are put in the field for soil nitrate measurement, and the robotic sensors that can provide information about the water flow rate and the nitrate, and put them all together. The analytics platform can generate a heat map with high resolution. For example, at a subfield resolution, this heat map can tell us about the water flow rate distribution as well as the nitrate level distribution through the drainage pipe across the whole field. So farmers will get the heat map that tells them the information like the water flow rate distribution and the nitrate level distribution. I think both farmers and co-op can use that. From the farmer's side, if they have the sensors or the robotic sensors that are cheap enough, then they can hold the sensor, send that into the pipe, and then let the robot tell them the water flow and the nitrate level inside their pipe. So this can give farmer idea about where is the hot spot. And for the co-op, they can commercialize the sensor and then use the sensor for service and telling farmers and different stakeholders about the nitrate distribution and water flow distribution on their farm. And this also can provide the information for the drainage system companies who are designing these drainage systems with better layout and with better planning for implementation on the field of farmers. The sensors developed through this project can not only be used for the robot, but also can work on their own. So farmers can put the sensor on their main tile and the farmer's tile to look at the nitrate loss from their field. This is a good way to control the fertilizer application to their farm. When the sensor is small enough and the price is low enough, farmers can put the sensors into their drainage tile, and then they will know what is the water flow and what is the nitrate loss from their field.
Hello, my name is Christian Lidke. I'm one of the graduate researchers from Michigan State University Smart Microsystems Lab, working on a pipe inspection robot for the agricultural drainage pipes. My colleagues are Xinyu Zhou and Dr. Xiaobo Tan, who is our advisor. We've been working on this pipe robot prototype in order to go through the drainage networks. We have these fins which form these sort of V-shaped barbs. And as most barbs are, they want to go forward, but as you pull them out, they'll get stuck. So that way, as our robot contracts itself, it sort of moves like an inchworm along this pipe. So we're going to start with a little demonstration here, as you will be able to see it move somewhat slowly at first into the pipe. Now, once it's inside of the pipe network, if we wanted to change directions, we would move those fins that I showed into the other orientation. That way our barb faces the other direction, and as it does that same motion back and forth, it'll pull itself back out of the pipe instead of pulling itself through the pipe. With this, we hope to be able to carry various sensors like water flow sensors, nitrate concentration sensors, and cameras through the pipe network. Also, with robot tracking where it is, we can give location information for each of these measurements, allowing us to create a map not only of the tile network itself, but also nitrate values and flow values throughout the entire network. Hopefully allowing for more informed decision making when it comes to smart drainage practices to reduce the nitrate loss. So this robot and its motion mechanism are specifically designed for corrugated pipe at this time. So that means if I turn it on, it's not actually going to move, as there's nothing for these fins to catch on. So you see it contracts, but it really just sits there and slides on the table. Without these fins to catch on the corrugation, it's unable to move. Now we're hoping with future developments to be able to work with like clay tile and other smooth wall pipe networks, and also to expand the diameters that the robot can work in so that it adapts while in the network without having to have any kind of parts removed or changed. So we came here to Iowa in order to show this robot and our current work to farmers and tile contractors so that we could get their feedback both on how they thought our current progress is going and what developments we might need to make in the future to create a product that best addresses their needs and concerns. So some of the most interesting things we learned was not being familiar with the history of tile installation, was learning about things like concrete and clay tile. We did not know that, being engineers and not farmers, which meant we need to make sure that this robot can function in all those different environments. We also weren't sure about things like different diameters, which was something we were told that pipe diameter can change throughout the same network. Other than that, they seemed quite interested in the being able to get instantaneous nitrates measurements, thanks to our colleagues working at Iowa State on the sensor. And there was some concern about either getting stuck or water pressure moving the robot. So we were going to keep those in mind as we develop it to make sure that we don't block the flow while we're doing our runs. Next for us working on this robot is primarily we're going to first try to get the robot untethered, which means we're going to get our batteries, our circuit boards, we're going to get it into the robot, try and get then start getting the sensors included so that we can maybe start running this in some real tile experiments. This will also include some waterproofing, because right now, obviously if you put a circuit board underwater, it's not going to work very well. But so that's our push right now, is we'd really like to be able to get this into some more realistic experiments rather than our little in-lab substitute right here. The larger implications of this project, to me they're very interesting because it connects my work with well, not just my work, our work, with a tangible effect on a community. The water quality issues here in Iowa, if we can help provide a cheap and easy solution for farmers to make decisions to help that, I think that'd be a great effect for our work to have, not just have a robot sitting in a basement somewhere.